Hopefully all these animations will work. I'll be coming in and out of the presentation to show some of the animation slides. And also please interrupt me if you want any further questions. There's quite a few slides here, and tell me if the pace is wrong. But I'll be discussing the earthquake itself and its relationship to the growth of the Himalayas, the topography in the long term. And then also important for this sort of societal concern, that the continuing and remaining seismic hazard that still exists both around Kathmandu, Nepal on a wider scale, and the whole Himalayas. So this is not just work done by myself. It involves a large number of co-authors and collaborators, people who provided me also with material for these slides. It is really an international endeavour to understand various parts of the earthquake cycle, as well as numerous colleagues here within Oxford. And it's funded largely through grants through the UK from the Natural Environment Research Council, through these sort of various groups here. So my talk outline, I'll start with the background to earthquakes just more generally and seismic hazard, before then focusing in on the Himalayas themselves, the tectonics, the building of mountains, and the earthquakes that form them. And then going into the Gorkha Nepal earthquake of last year, and how that relates to the long-term growth of topography, before concluding on the sort of remaining seismic hazard and some comparisons with other earthquakes. So the human population is growing, expanding and densifying into these urban megacentres along the Alpine Himalayan belt. And that's led to an increasing number of large earthquakes that have huge number of fatalities in the past 100 years, and that's increasing. And we're often surprised by the exact location or magnitude of these events. There's a long time between earthquakes on any given fault on the continent, so we have to try and measure and understand these earthquakes wherever they happen, and then try to apply that knowledge more locally, and try and interpret the subtle telltale signs in the geomorphology, how the landscape looks for those signs of activity. And also try and incorporate different data sets in trying to build up, instead of using, say, earthquakes in the past, look at how quickly the crust is deforming today using GPS and various satellite techniques that I'll go into, to try and understand this building up of pressure in the continents that eventually must be released in earthquakes. Places like Central Asia, which are deforming quite quickly, they're being squeezed, and there are a large number of huge cities around its edges. So it's been the anniversary just recently, the 5-year anniversary of these sort of big subduction zone events like Tohoku, magnitude 9+, that happened in 2011, that caused a large tsunami to inundate the island of Japan. And it's also just recently in February the 5-year anniversary of the Christchurch earthquake. That was much smaller, magnitude 6.3. This is the dust rising from the centre of the city, much smaller but still had a large impact. There were big ground accelerations here that were twice the speed, twice the accelerations of gravity, so it's so large here, having an impact on the city centre. So there's a range of scales there of magnitudes that I'll go into later, what magnitude 9 and 6 are in comparison. And the last sort of decade and a half or so has actually seen big earthquakes to strike continental zones and cause a huge amount of damage, resulting in often many tens of thousands of fatalities in places such as Bam in Iran, Pakistan, in Kashmir, which I'll come back to later, and also Wenchuan, Sichuan in China, resulting in over 80,000 deaths, and then also the Haiti earthquake. Now, if we compare these to other sort of disaster types, the number of people often affected by different things such as drought and flooding and storm is usually quite large. But then when we compare it to earthquakes, the fatality rate as opposed to the number affected starts to swing the other way. And in fact, on this graph produced by the centre, they've actually cropped the scale bar, and if we put it back to its sort of right magnitude, it's sort of showing in the sort of first part of this millennium that the rate of deaths was about 50,000 per year, so outstripping many of the other sort of disaster types. And if we look back now on the decadal timescale, this is very small, and I'll just point out this is the top 40 catastrophes in the last sort of half a century. They're predominantly results of earthquakes here, about half of them. And then if you compare it to the sort of financial costs, this is a compilation, if we then see where the Nepal Gorkha earthquake, it sits here in the table, about 9,000 fatalities. This is a compilation by the reinsurance industry. If we look at costs then the costs are actually the reinsured costs, not the actual true economic cost, but the insured losses. That's usually dominated by other natural hazards, not the earthquakes shown in pink, and they're in the developed world where the reinsurance, there is an insurance market where structures and people are insured, and you don't get that in the developing world. And then if we look at this on a much longer term timescale now over the millennium, you can see in the past, the first half of the millennium, these sort of events that killed a huge number of people were about 5 per century, but that increased through time, and the sort of rate at which we're going now will see events killing more than 10,000 people occurring about 65 in this century alone, so more than every other year. So often a question is, when we see those kinds of statistics, are earthquakes becoming more frequent? Well, they're not. This is a compilation from the last 100 years. It's pretty static. They're very variable. The number you get in any year varies a huge amount. You need to look at it over a long-term average, but they're not increasing through time. That's not the reason. It's increasing populations and their vulnerability in the built environment. So now I'm going to go through the sort of plate tectonics, the background, the sort of geology, the earth sciences side of it. This is our world as often viewed by us, looking at the topography and the earthquakes that have struck them in the past sort of half century. Now it's a case of joining the dots with many of these on the ocean, so it's quite a simple exercise. That delineates the edge of the plates, where they're sort of broken, they're snapped, where they can build up pressure. But on the continents it's a bit more spread out, and I'll come back to that a bit later. But in a nice sort of textbook colourful diagram, these are the sort of names of plates, and the ones we'll be interested in today are the India and Eurasia plates most. And again, another sort of textbook view of how the world works is this sort of approach to the sort of cycle, the turning over the Earth's surface, where the crust and the plates are formed at mid-ocean ridges. They spread out on a sort of conveyor belt system, and then they collide into continents. Plates subduct down, and you get large mountains at the edge, big subduction zone events here, and perhaps earthquakes in the continental interior. So that sort of view of plate tectonics, and you get this sort of spreading type 1s, convergent zones, and transpressional. So if we look at this now and the sort of distribution of earthquakes globally, we've got our strike slip ones, where one side of fault moves sideways relative to the other, spread around the Earth here, shown in these black and white focal mechanisms. They sort of show you the type of earthquake. These normal faults, where you're pulling apart the crust, pulling apart the plates, so you see these down these mid-ocean ridges where you're creating the crust and the plates. And then when you're bashing these plates together along the ring of fire, these subduction zones that give you the sort of biggest ones, but also in these continental interiors here. So you can see nice join the dot lines around the oceanic plates, but a much more messier picture in the continents. So that's also a view of the way that the earthquakes are sort of on a global scale seen. And how do we actually measure these things? Well, actually, in the past, in China, an area that's had a large number of earthquakes and will continue to do so, they have this rather innovative way of doing it based on balls dropping out of a dragon's mouth into fog that would even tell you the sort of direction from which it would come. And basically 2,000 years of development haven't fundamentally changed the way in which you're trying to do that. You're trying to get at the shaking of the ground and telling you the sort of direction that this shaking's come from. And this is an early seismogram from 100 years ago, showing the recordings in Germany based on an earthquake on the other side of the world in Japan. And then sort of today, the current state of the art for seismometer work, for the global seismic network, are these stations spread around the world. There are even more on a local basis, but this is the global network. And given an earthquake, and using these triangular stations, you try and pinpoint where that earthquake occurred by the time it takes that energy, the shaking, to reach those different stations. So it's a sort of triangulation. You're trying to work out where in the world that's come from. So just to go into those waves, these are things that you might have come across. This is our Earth, and this is our Earth model, the whole Earth sliced through. This is a bit of material that's going to be deformed by the passage of this seismic energy going through. One type of these P waves, pushing backwards and forwards. Okay. And if we look at how long it takes for different parts of this wave to get around the Earth, so this is the time it takes to travel and how far it goes around the Earth, from an earthquake up here round to, say, our first station. This is the wave, the P wave, diving through the Earth and coming up at this seismometer so we can measure it. And it takes a certain amount of time, sort of tens of minutes to go that kind of distance. Seismometer further away takes a bit longer, not twice as long, because as the wave dives deep in the Earth, it actually goes faster because the material is denser. It's able to propagate the wave more efficiently. And there are also the secondary waves, the sort of shear waves you get. They're a bit slower through the Earth. They don't travel quite so fast. They take a bit longer. And then we have the surface waves, the Rayleigh and Love waves. These are the ones that travel, if you see there, they were travelling along the surface of the Earth from the source, the earthquake, to the seismometer, and they're a bit slower themselves. They go about 3 kilometers per second, so still very fast, but slower than the other waves. And they're in fact the ones that do the damage, largely. So again, taking another perspective view of our earthquake, and our seismometer, or wherever you're standing. P and S waves dive through the Earth, little and bigger waves, and then the surface ones come later. They're slower, but they're a lot bigger amplitude, a lot bigger shaking. So that's also sort of the things that do often the damage. And the damage is usually a lot closer than this. So once you're this far away, you actually need sensitive instruments to be able to measure it when you're on the other side of the world. When you're much closer, it's obviously the things that cause the damage. So I'm going to be talking a lot about earthquake magnitudes as well. So I want to give you a sense of scale of that. Imagine you've come across the different magnitude scales and know that there are big jumps in them. And it's probably easiest to see this graphically and also to address how often they occur. So globally, between magnitude 5 and 6, there are about 1,300 earthquakes per year. And magnitude 5 is about the smallest you can measure from the other side of the world using that global seismometer network. And people in the UK are often worried if you get a magnitude 5 and a chimney pot might fall off. That's the kind of earthquakes we tend to experience, very minor damage. So this dot here is what I'm saying is our relative size of a magnitude 6. Going from 6 to 7 now, again, first of all worrying about the UK, the biggest one that's been seen in recorded history, so a 100-year timescale, is 6.1 offshore UK in the North Sea. The Christchurch one, the dust rising from the city centre, that was a magnitude 6.3. So that's just a bit bigger than this dark black dot in the corner. And then the Haiti earthquake that killed probably between 100,000 and 250,000 people was this magnitude 7. So the lighter blue square. If we then scale it up again, you'll notice that the number has dropped. You get fewer of these bigger earthquakes, but they have more energy in them. Scaling them up again, this is what would be a magnitude 8. So there are only about 15 earthquakes between 7 and 8. And the Gorka earthquake sits towards the sort of red end there at magnitude 7.8. So the earthquake last year was that sort of size. And the deadliest earthquake that we expect to have occurred, it's hard to tell because it was 500 years ago or so, was in China with an estimated sort of 830,000 deaths. And then even getting bigger though, this is the energy released in the earthquakes such as that Japan earthquake, the Tohoku earthquake with the large tsunami. That's the kind of energy, extra energy you're talking about there. But it's still not the biggest. The biggest one recorded is magnitude 9.5. I can't even show you that. That would take up quite a few screens. But what you'll see is the magnitude scales change a lot, but the numbers of deaths is quite variable. It's not just how big it is, it's where it exactly occurs and also the built environment people are in and how far away they are actually from the fault, whether the fault gets to the surface. So big variations there. But these are the sort of numbers you want to be remembering, the sort of 6, 7s and 8s when I speak about these events later. And then also, what causes these earthquakes? Well, their motion at depth on a fault plane. Now, these are often hidden. That's part of the problem. They're often hidden hazards. But here's one that's beautifully exposed in Greece. Here are where we take the undergraduate students there for scale. This is a fault that's actually made it to the surface and then has been revealed by the removal of sediment from on top of it. But it records the sort of past earthquakes that have occurred on it. And these lines, these are the scrape marks that have occurred in the earthquake, they're the striations. So if we put the sediment back on top, this is what the other side of the fault would have been like. An earthquake consists of these sort of jumps as the fault slides, and then you wait, and then it slides again, and then you wait. Now the sliding takes seconds, the waiting is usually hundreds of years, and the amount it moves and when it moves, we can't predict beforehand. So that's one of the limitations, that's why it makes it so hard to deal with this kind of phenomena. And that sort of sliding is if you imagine you've got a brick on a surface that's rough and you're trying to pull it with a spring. It requires some force to do it, but it won't necessarily move until that force has built up enough that it slides, it overcomes that friction. And that friction can often generate a lot of heat. This is a picture through a fault, a sort of small scale, but showing this black material is actually called a pseudotachyte. It's actually melting that occurs due to the friction and the heat that's released in an earthquake. So what tends to happen if we look at the evolution of a fault over time, the amount that it slips, most of the time it's doing nothing and then it suddenly jumps, doing nothing, suddenly jumps. You get this rapid slip and then this slow strain accumulation in the crust that's then building up the pressure that has to be released over time. And this time is usually many hundreds of years. But on average we often measure a long-term slip rate if we go and measure these things in the field. So often we're asked a lot about earthquake predictability and trying to get at why we can't foresee these things coming. Now if we take this extreme case, which doesn't happen, a periodic earthquake, and we look at the stresses through time and the amount of slip that occurs on the fault, if we knew where the starting stress or the pressure was and where you reached and it eventually snapped it, like putting an elastic band, the longer and harder you pull it, the more likely it is to snap. If we knew both those things, we could predict when it was going to break. And we could go through that cycle, repeating it again, knowing when it's going to slip again and again. That would be very periodic, very regular, very predictable. But unfortunately, it's nowhere near like that. If we knew the breaking stress, but not how much of that stress or pressure was released, then we would be able to predict when it would go, because you'd watch it and eventually you knew the pressure had built up, that it would be able to break. So that would also be useful, but that's not how it works either. And another thing that seems to maybe go a bit further, but it still doesn't make it possible to predict when, is this case where you don't know when it's going to snap, but you probably know how much slip is released, because it's been building up the pressure. The longer it builds up the pressure, the more it's got to slip to release it. So you don't know when it's going to happen, but it's going to drop down to some amount, so you know how much slip there should be. And that's sort of how it's often viewed in some places, and you can try and use that theory in the Himalayas, but it gives you no use on time. You just can't say when this is going to occur in time. It depends when it breaks. And another thing about the sort of earthquake side of things is the difference between the continents and the ocean. So I showed you the sort of very biggest earthquakes, these blue ones that occur on plate boundaries, so that's like the Japan earthquake. They often kill a large number of people, shown by these circles down here, but they're relatively infrequent. The thing that seems to do more of the sort of damage on average are the more frequent, more common ones in the continental interior. So this smattering of earthquakes here in the interior, there are many more of them. They are smaller magnitude, but that's often where people live. They're obviously on the continents, the faults are going to be a lot nearer to them. So that's why they have a bigger impact. So if we focus in now on, and I just want to say that this is often coming from collisions of these plates into each other that have built up the pressure in these individual areas. And if we focus now on the Alpine Himalayan belt, this is going back to where our earthquakes are again, we've got a relatively stable continental interior of Eurasia where you don't get many large earthquakes. They're all, if you get any, they're tiny. It's pretty rigid, pretty solid. Then you have these other relatively solid plates of Africa moving northwards into Eurasia, creating this set of earthquakes up here. Arabia, again into Middle Asia here, creating the deformation in Iran and the Zagros. And then the one we're particularly concerned with today is India here, moving northwards into Central Asia, about 40 millimeters per year, that's building up this collision zone here. So it's a sort of car crash crumple zone of plate tectonics here. very wide area with a large number of earthquakes, some of which are very big. Now that's the sort of motion that's going on today. It's all very slow, but it's actually been going on for quite a long time in this region. So this is that sort of picture of India and the Tibetan Plateau here in red. But 70 million years ago, India was actually down here relative to Eurasia. So if we look at now the time scale, 70 million years, and we take 2 points at the tip of what was India then, okay, and look at how far away they are from now, so about 5,000 and 6,000 kilometers. Over time, that continent has drifted, at first quite fast and then a lot slower, to then be in the position it is today. And the sort of rates we're looking at now are sort of 40 millimeters per year. So India gets closer to Eurasia by about that much every year. In the past it was a lot faster, about 3 times that, but it's slowed down, and it's slowed down because it's bumped into something. The sort of force that this exerts on it slows it down. So if we look now at this over time, this is playing sort of a snapshot of a cartoon animation through time. India bashing into Eurasia through time, these are all slices. It then builds up the topography. You've got a subducting plate that then you lose or you don't. There's actually quite controversial scientifically, various aspects of this model. We're not quite sure because it's over a very long time. So let's just play that again. And there are actually probably continental slithers in between these. It wasn't just an ocean on its own. The old ocean was called Tethys there. They used to exist. But that's been slowly grinding away over those millions of years, building the topography today. And that's how you get things like Everest. This is Everest in the background here. That grinding of the plates together forces up material, and in the long term you build mountains as high as almost 9 kilometers here, as well as the Tibetan Plateau behind it, which is about 5 kilometers. And we often want to understand these processes that not only just give us the earthquakes, but also the topography we see on our planet today. And one of the ways of measuring how fast these plates are all moving around in the past sort of couple of decades or so has been with GPS. And this is actually an instrument installed in Nepal. It's courtesy of Jean-Philippe Avouac and his team that have installed many of these, many people we've worked with, measuring how fast this bit of the Earth is being deformed using GPS satellites that are always going around. And this receiver, GPS receiver, just like in your car but a lot more accurate, is asking where is it, and over long term you can see how much that changes through the year in, year out. And if you have that in many different places, these sites installed, or scientists going out and measuring them every year or so, you build up this map of velocity vectors across this whole area, saying how fast each point on the ground is moving with respect to some stable bit, which we'll say is Eurasia here. How fast India is bashing in, about 40 millimeters per year. Here's the sort of scale bar. And you can see the sort of scattering of the crustal material. It fans out and moves around here into eastern China, swings round, the sort of motion of the Earth's crust. But to accommodate this, within this, there are lots of these faults marked in red. They've eventually got a crack under the pressure, and that's what we're concerned with today. We want to look at how fast this is occurring over this part of the Himalayas. So if we take a section through here, looking across both this topography and how fast these GPS instruments are moving, we've got the high Tibetan Plateau and the high Himalayas here, and topography above 6 kilometers. And if we just focus in on the red lines, they're the GPS velocities, how fast they're moving in millimeters per year, so 40 millimeters per year, that much relative to Eurasia. And over this zone here of the Himalayas, it drops by about 20 millimeters. That's showing you the Himalayas are absorbing that much of the collision zone, that much of the crumpling in this sort of crash. The rest of it is accommodated. The other sort of 20 or so millimeters is accommodated across the rest of the Tibetan Plateau and further north into the collision zone. And this has built this high topography of 5 kilometers of plateau and some higher peaks at 8 kilometers. Now it's possible to use this data to then ask some questions about the nature of the main fault in this, which is the Himalayan thrust here. Using all these GPS vectors and showing the sort of 20 millimeters of shortening, the crumpling, or the building up of pressure really, it varies slightly along the Himalayas. But using that, you can ask how much of my fault is stuck, building up pressure, and which bits are freely sliding. So in the shallowest part of the crust, the fault is locked, okay, building up this pressure from the collision. But deeper down, it's hotter. So actually you get creep on that. The minerals slide over the years, and they can accommodate this 20 millimeters per year of crash. So they gently move. But the upper bit is locked and is building up this pressure. And that's what this red and white map is showing. This part of the fault, which is basically all of the shallowest part, is locked fully. It's 100%, that is, number one, 100%. And all the bit north of it is stably creeping. The deeper, hotter bit is stably sliding and contributing towards that build-up of pressure. So we know that most of this area has to crack. It has to break in a fault. So here's a sort of animation taking just a section through here of that sort of process of India bashing into Asia, building the Tibetan Plateau and the Himalayas, looking at how this topography changes, how it pressures and which bits are creeping. So this is deeper and hotter creeping, and this bit is locked at first. So this is our fault, joining Eurasia onto India, the interface between the two. So hopefully this will just play. So you see this is not moving, but this bit is moving. The two sides of it is moving. You get small earthquakes, then a big one. Eventually the pressure builds up and it releases that in one go. So let's watch that again. Okay, moving, locked, and then snap. And then you get this recoil as the upper part of the plate slips back on itself towards India. So that's the earthquake cycle. You're sort of building up the pressure there through time in the collision. This stays locked but is getting more and more stressed. This bit stably slides, but eventually it's got to give up. The problem is we just don't know when. We're trying to look for telltale signs, maybe small earthquakes, something like that, but nothing's been very good at giving us the time at which it goes for the big one. And that's a big limitation. So we can also look at what we can learn from the past, as well as those measurements today, what's happening over the last 10 years, the build-up of pressure. We've also got a record of the past. This is a compilation of previous earthquakes along the Himalayas, in the pink circles here with the dates a bit small. This is a compilation from Roger Bilham, showing those in the last couple of hundred years where these earthquakes are thought to have occurred from historical records, largely written records of damage, things that would have been in the newspapers at the time or in diplomatic couriers, things like that. And then more modern ones like the 2005 earthquake here. Now, as I said, this is a result of this shortening, 20 millimeters per year. It gives you this long Himalayan fault that's 2,500 kilometers long. Okay, seems to be breaking up in smaller bits. A concern would be if it went in bigger chunks than it does. You'll see some of the potentially larger earthquakes in the past. And I'll come back to it later, but the Kashmir earthquake, magnitude 7.6, so smaller than the Nepal earthquake last year, resulted in 10 times more deaths, 87,000. So they're in a similar collision zone, but had a very different impact. And I'll show you the reason why there's such a big difference at the end. But here we have the one that last had a sort of impact on Kathmandu, the 1934 event. So this was the Bihar Nepal earthquake, bigger, 8.1, bigger than the 7.8 last year, 1934, that caused extensive damage in the city. And in fact, there are records going back that there have been earthquakes that have affected this part of Nepal quite a few times in the past. You'll see there's no regularity there. There's no predictive power in saying, oh, there's 80 years there, 100 years there, 150 there. There's just no exact regularity, but you know it will keep happening. That's the important thing. You just can't use it as a regular predictor. But often that seems to be around 100 years. So now focusing on the last year's event itself, Kathmandu here. The main Himalayan frontal thrust lies along here, and these are the older thrusts in the system, the older faults that used to do some of this collision zone. And this is the sort of area of the map that we're looking at down here. The 1934 is here in the east. This is the zoom in we've got. Now, before the earthquake, the only sort of significant earthquakes are sort of microseismicity, smaller earthquakes, lay in a band to the north here. And that's thought to be the zone between this bit that stably creeps, so always moving, and the bit that's locked. It's the sort of bit that's in between, so it goes off in little small earthquakes. It seems to form a band that seems to be at this transition from the fully locked to the fully creeping, this sort of zone here. So this is the top of the fault, and this is the bottom. So Kathmandu sits above this fault. And in the earthquake itself, it nucleated, it started out here in the west and propagated eastwards for about 150 kilometers, north to Kathmandu and beneath it. Okay. So researchers using the seismometers from around the world can get a picture of where the rupture was through time. So this is time, where it starts, where it releases its energy and its slip as it goes past Kathmandu. So that's it passing the capital. So it takes many sort of tens of seconds to rupture along the 150 kilometers or so. And the impact right above the epicenter, where an earthquake starts, is shown here in this satellite image from before. So this is from 2014, the end of 2014, a village sat on a ridge, Barpak. The earthquake started beneath it, and you can see the impact in a satellite image taken after the earthquake, the total devastation in this village. This is a picture on the ground from a colleague showing the impact from the shaking and the kind of destruction you get. You also have secondary hazards as well as the shaking of buildings. It shakes the landscape and you get landslides. And there was this village of Langtang here at the bottom of these steep slopes, image from before and then after. The shaking in the earthquake caused this landslide to come down the mountain and inundate these villages. And a picture from the air of this shows the kind of air that was covered with this landslide deposit, and it rushed down the mountain at hundreds of kilometers an hour and then actually shot up the other side as well, completely covering all the buildings that were there. And this is a sort of landslide map then of what was mapped after the earthquake, where these sort of landslides occurred, the sort of density shown in these rainbow colours, hot red where there are lots of them, relative to the epicenter, up in the highest topography usually. These slopes are very steep. They're built up over the long time by this collision, but the shaking causes the slopes to fail and fall down. And then Kathmandu is here to the south, so it's all south of where the rupture was, south of where the landslides were. And if we look at then the distribution now of the intensity of the shaking as assessed from the sort of damage to the buildings and things like that. For this kind of earthquake, it is surprisingly low. These are sort of 6, 7, so they're moderate to damaging. Okay, they're not destructive. Okay, not total destruction. Given such a big earthquake, this might be viewed as a bit surprising. The devastation was not as large as was immediately feared after the earthquake. And we'll come back to maybe why that was so in a bit. But there was also something unusual about this basin as well, which we can see using the GPS. I'm just going to show you a picture now of where these GPS are in the Kathmandu basin. Okay, so you've got sort of the hillsides around, and then you've got a basin in the interior. It's an old sort of lake bed that's filled up hundreds of meters, 600 meters thick worth of sediment, softer than the sort of mountains around it. And there are some instruments that were placed here before, knowing that this area is likely to be seismically active. Something called an accelerometer that's very good at measuring sort of shaking, and then these GPS that can measure the shaking and also the total movement compared from before and after the earthquake. So I've just got a video here from a colleague showing what was happening in the city centre. See if this actually works. Is that displaying okay? So there's a couple of colleagues in the US. Now this is a picture, CCTV camera and a GPS location. Imagine that sort of GPS, how much it's going to move. See some shaking. This is about noon on the day of the earthquake. Some shaking, the birds fly off, and this GPS is moving. You see the people are startled by the earthquake. And then you get this swaying, a very unusual shaking backwards and forwards. 1, 2, 3 times. And it carries on. Now what this GPS is recording is how much that site moved east and how much it moved south. Actually physically how much it moved in the seconds of the earthquake. So you can see it lurched to the east by a metre as the earthquake came through, but then lurched back westwards, and all this time was going to the south. And then it reverberated. There was this resonance backwards and forwards about 6 times before it settled down at some place away from where it started. So we'll just watch that again. You can see it's done backwards and forwards, all the people moving about 6 times. But you can see actually, despite that huge amount of movement, there's very little building collapse there, there's just a bit of rubble. And that was the sort of, you know, the amount of building damage was less than you would think for such a big earthquake. So we now look at, that was from an instrument here in the basin, within the basin itself. Just taking a snapshot at the end there. The GPS site has moved south by over a metre from where it was. The earthquake's permanently moved the ground a metre south towards India, and also westwards a little bit, but not a lot. It's mainly the southward movement of the upper plate in this earthquake. And this can be seen very easily on the different GPS. These are records of how much that movement of those GPS stations in time from when the earthquake started, when the pulse actually hit, and then the total amount. So if we look at this, this is for the north of Kathmandu on solid bedrock. This is the 0 line, and then the actual total displacement. After the earthquake's finished, it's all done, moving 45 centimetres west, 1.8 metres south, and up as well. That's another important component. This has moved Kathmandu and the mountains north of it, immediately north of it, up. And if we just track this eastward motion, goes up, down, and then is pretty static. That's the bedrock. Okay. Now the difference in the basin, this ancient lake bed that's really thick, is in this pattern of motion. Goes up, down, but then reverberates 6 or 7 times of about 4 seconds period. That's how long it takes to do each of these sways. So again, if we compare, the displacements are slightly different from the north. It varies in space. That's the kind of amount the crust has been jacked up and shoved south. So if we compare then those 2 different ones, the one I showed you earlier is this one in red that comes round and then goes backwards and forwards. That's the soft sediments. The blue goes around similarly but doesn't shake backwards and forwards the same. Okay. It doesn't reverberate, and that's the difference between being up here and in the basin. So those near field effects are quite important to try and understand the impact it's going to have on the buildings. You need to know the sort of thickness of soils, the thickness of sediments, as well as sort of a bit of the nature of the earthquake. And that's not always easy to tell before. And if we look at that accelerometer, the thing that tells you how fast things jump compared to gravity, the accelerometer in the basin showed accelerations peaking at 0.15 of a g. Okay, so you feel it, you saw everyone feeling it, but it's not the speed of gravity. You're not being flung weightlessness. And I showed you that Christchurch event. The peak ground displacement from that earthquake that chucked all that dust up was 10 times bigger, more than 10 times bigger. It's 2g, 2 times the speed of g. You would have been lifted off your feet with that. So there's quite a different earthquake. It's bigger, but the accelerations haven't been as extreme. They were extreme in these sort of longer periods, that big shaking, but not in the shorter periods. Let me explain this sort of picture. This is how much you're being accelerated at different frequencies or different periods here. So 1 second. The ones I showed you were 4 seconds, so they're about out here. Now, purple is what would be predictive for sort of the ground motions in an earthquake. And these lines are the sort of measurements from all those different instruments. And they sort of match for the longer periods, so more seconds, lower frequency. That was sort of right. But there's a missing amount in what's called these high frequencies. From the predicted, the real life was a lot lower, 4 times lower than it would have been expected. So you've lost those high frequency shaking in this event. Now that's important because the different frequencies or the different periods affect buildings in different ways. The things that sort of resonate, the longer something is, you need a longer period for it to resonate. So if you've only got a couple of floors, you're worried about energy being high frequency shaking. If you've got really tall buildings, skyscrapers, you're actually worried about slower, longer period, bigger amplitude motions. And these are the sort of frequency ranges. Here you're worried about bigger buildings. So just to pictorially show that of this structure in Kathmandu, but before and after pictures, this is 10 stories, that sort of level, was actually destroyed in this earthquake. It was big compared to the shorter buildings around which didn't suffer catastrophic collapse. Because it felt those longer period shaking and started resonating and swaying and eventually toppled over. Whereas the smaller buildings sort of ignored that. They just went with the flow, literally, went with the motion. And that's similarly what happened. This is the same structure that was destroyed in 1934 and subsequently rebuilt. So that earthquake had a similar sort of impact on tall structures. But it doesn't seem to have damaged all the shorter structures in Kathmandu. So this earthquake, in some ways it was fortunate it didn't have that high frequency content. It ripped in a sort of gentler, lower frequency way, so it didn't destroy all the buildings that were about 2 or 4 stories. It was only going to destroy really tall buildings, of which there aren't particularly big skyscrapers in Kathmandu. You can have a big skyscraper that can survive it, but it has to be seismically resistant and it will sway. You can see pictures from the Japanese earthquake of very big skyscrapers swaying. They don't necessarily have to break if they've been seismically reinforced. So what we want to do is understand the nature of the faulting beneath Kathmandu as well. So going back to our picture of Nepal, the faults and the thrusts that exist in the landscape, and we take a cross section, we want to understand the nature of the fault at depth. So this is a sort of geological picture of India and Kathmandu and Tibetan Plateau, showing all the various sediments in it. And there are various parts of this earthquake we want to understand. What has been the activity, if any, of the thrust nearest the front? How is the slip accommodated really quite deep down on the structure? And are there any, how do we sort of understand how we grow the topography in the long term? And was there any motion on other older thrusts in this that were active many tens of millions of years ago? Do we see them being reactivated or do they stay quiet? So returning back to our picture in this event, there's that microseismicity, the fault locking, and then the distribution of aftershocks. So they're further in the north, deeper down on the earthquake here, and this was the aftershock that occurred at the eastern end. So where it continued on 2 weeks later, the magnitude 7.3. So if I go back to the sort of GPS, these are the measurements, those GPS sites. There aren't that many, and the ones outside of the earthquake zone didn't really move, because that's not where the earthquake happened. It's only the few that were in the earthquake zone that, remember, they moved south and slightly to the west. They all roughly did the same thing. And they also moved largely up, except this one to the north that actually moved down in this earthquake. So the GPS, there are only about 4 there that show anything, and as well as using the GPS satellites, there are other satellites you can use. If I zoom in on this area now, look sideways at it, another satellite is a radar satellite that takes a picture of the ground before and a picture after, and builds up a contour map of how much the ground has gone up and down, instead of at a few points, everywhere. So this is just like a topography map, what's gone up, and you count the contours. Each contour is 10 centimetres, and there are 11 of them, so that's gone towards the satellite over a metre. So it's a map of everything going up and down everywhere in the earthquake, over scales of hundreds of kilometres. And similarly, up here in the higher mountains, you count them, but they're going the other way actually, the contours. It's moving down away from the satellite. That bit's actually sunk down in this earthquake, not gone up. So we've got these pictures covering the whole half of Nepal, showing this up and down motion. There's motion towards the satellite here. We can use all these observations to build up a picture of how much the ground has moved beneath you. And in fact, one of the main things that we found was that this is a very smooth picture. There's no sharp motion right near the surface at the fault, the main fault through here, the main frontal thrust. The fault's not reached the surface, otherwise we'd see a sudden change from red to white here. These are all very smooth. That's telling us this fault, the slip, is buried at depth. The only thing we could find was in this bit here, away from the main thrust, actually behind it. And this little bit of the thrust only moves centimetres. It didn't do the many metres, it just a little bit of slip. That's all you can see from this earthquake at the surface as a fault offset. And there's nothing too obvious in the landscape. That's where it traces through. It's about 20 kilometres wide. And we can sort of see it's only a few centimetres. It may have grown a little bit after the earthquake. You sometimes get faults slipping a bit more. But really, you're not seeing much for such a big earthquake. Now this is important because there's another field of the science trying to look at past earthquakes called paleoseismology, and this relies on the fault slip actually reaching the surface. This is an example further west of the fault scarp itself. This has been built up because the fault reached the surface. The fault actually comes through here, but you can only dig a few tens of meters. You can't go down many kilometers. So this technique relies on being able to measure the earthquakes to reach the surface, and it looks like even magnitude 7.8s don't have to break the surface, whereas you would expect that in many parts of the world, something that big to have got all the way through. So this is a compilation of some of their work across the whole of the Himalayas, trying to find the evidence by digging trenches into the ground of where these earthquakes happened in the past, trying to go longer than the historical record shown in green, further into the past by dating radiocarbon material to actually get the time when that fault rupture broke, to try to look at big earthquakes in the past, potentially ones from the 1500s or even as far back as the 1100s, dating the old material that's been broken by the fault reaching the surface. So that's one ambition, but it doesn't necessarily get all of our earthquakes. So the catalogue going that far back doesn't capture all the earthquakes probably, but it'd be useful maybe at capturing the really, really big ones. Also want to understand the relationship with the longer term topography, how we build the mountains in the long term. This is one of the few areas that we can compare what went up and down today with what was happening before the earthquake, through a levelling profile from the Nepal-India border all the way up to the north with China. This profile from the sort of 70s to 90s showed that down here there was a couple of millimetres of uplift over the decades every year. It was slowly building up, and up here about 8 millimetres per year. So if we take a profile through here, this is the topography from the fault at the front, that didn't move, the faults down here beneath Kathmandu, Kathmandu itself and the high topography. If we look at that motion, it goes up 7 millimeters per year, every year for decades before the earthquake. But the measurements we've made show that in fact in the earthquake, the bit at Kathmandu did go up, like all those GPS measurements showed you, but the highest topography was actually dropped down in this earthquake. So it's undone all that work. It's actually destroyed the topography by lowering it by 60 centimeters across the 150 kilometers north of Kathmandu. And we can use these measurements to try and get at what the fault looks like at depth, because we can't see it. We have to use this data to infer where the fault is, what its shape is, and how much it's moved. So we can use this data set to test different models of how flat and how bumpy the fault is at depth and how much it moved, and also this stably creeping zone. So this is locked before the earthquake, this is always moving, and then this breaks in the earthquake, the blue lines. So we can do that and build up a model now of what's happened in the earthquake. I've cut out now beneath Kathmandu. We have other data sets that we can use that tell us roughly where the fault should be as well. This is using sort of reflection where you bounce seismic waves off structures at depth. But our sort of picture of it is this fault model going from the surface onto a flat and then a ramp. It's sort of got a kink in it. And that kink sort of starts to help explain what we see in this earthquake. And once we've got that geometry, we can work out using the satellite data how much it's moved. So down here at depth, it's moved on average 4 meters, with some bits moving as much as 8 meters, all in this what was previously the locked zone. And as I said, we can use this then to explain how we build this topography. If we look at how much the ground goes up in the earthquake compared to this data taken decades ago from the levelling, we can see that we actually need this break, this kink in the fault, to push material up this ramp in the long term. If we didn't have it, we wouldn't be fitting that data, the green data from this levelling profile. So we need that ramp to explain it. So that's our sort of geometry at depth. We know it's flat and then it kinks down, and that pushes material up in between earthquakes. And we can also use this to then model what we expect the motion of everywhere to have been. So these vectors show how the Earth's surface moved in this earthquake. So up here on the plateau, not a lot. As you went further south, it went southwards and down. But once you reached Kathmandu, the ground was actually going south and up, okay, before it stopped here and there was no motion on the main thrust at the front. That's not yet slipped. So if we see this in perspective, in map view again, this is how our fault is at depth, the flat bit here going down from 2 kilometers to 14, and then it gets steeper here. Where that slip is, it all lies north of Kathmandu, okay? And we can overlay where the aftershock was. You can barely see that, but it was a relatively big 7.3 that broke the end of the fault. It carried on a little bit. And we can also compare where the energy was released in this earthquake from that earlier animation I showed you as it propagated eastwards, where the energy is released and how quickly it does it. And that sort of tells you the rupture went along at almost 3 kilometers per second. So we sort of, by combining all these different data sets, you can build up this picture of where the slip was, how fast the rupture was. And then the important thing that we can take home from this, that the slip was all north of Kathmandu. There was none on this shallow part of the fault here. Between 10 and 0 kilometers depth, nothing moved, okay? It's locked, it's in red, so it's building up pressure, but the earthquake didn't release that pressure here. In fact, there's quite a sharp break where the sort of fault slip ends here. It's much shallower. And that's a concern, because this is now under increased pressure. It's an area that's as big as this patch here, but it's not yet broken. What happens if it goes in one go? Can we tell when? No. But have we got analogies for this that are comparable, that show that sometimes you get an earthquake and then a few years later you may get another one? We do have a couple. They're pretty rare, but here's an example further north than this collision zone. So we were down here. This is now at the northern end of the Tibetan Plateau, a pair of earthquakes that happened in 08 and then in 09. Similar type of earthquakes, the ones that are sort of collision earthquakes. So if we zoom in on here, this was the area of the earthquakes. One happened here in 08, one in 09. a year later, about 11 months later. And what we wanted to understand was the relationship between these. Nobody lives here, so it was actually quite hard to know how close these earthquakes really were. They were separated by 15, 20 kilometres, but we want to know how are the faults connected. These are the sort of main faults in the area and the folds that you get from squashing the crust. So if we zoom in and use those satellites to measure where exactly the ground went up and down, the 2008 one says it was here in the northern portion, showing the ground going up. Then 11 months later, in exactly the same area, the fault broke. There's much more ground deformation, but the earthquakes were the same size. So that shows you the earthquake must have been shallower, nearer the surface to push it up. But they're in roughly the same location. So if we look at this now, the relationship of their fault planes, this one, the white one, and the later one in black, and look again at these cross sections across the fault. The deeper one is between 20 and 12 kilometres in 2008. 11 months later, the rupture carried on. It had a shallower earthquake here. Okay, so there was a hiatus, a break of about a year. Couldn't predict how long it would be, couldn't even tell if it was going to happen, but we've now got an example where there was an arrest in the rupture. And this break may have been caused actually by this other fault in the area. This fault maybe intersects this earthquake fault plane at about 10 kilometres and damaged the zone. So it made it hard for the earthquake to actually get through that damaged zone. It couldn't propagate through in one go. It took another year of pressure build up for it to carry on. These are processes we don't yet understand. These are just new, sort of relatively new observations of what's going on. And if we look at these slip patches, this is how much it moved in 2008. It just stopped at a depth of about 10 kilometres, this is. And it was a year later when the upper part of it broke. And these are much smaller earthquakes than the Nepal earthquake, but the worrying thing is if the sort of similar pattern may occur in this area. And in fact, this repeated earthquakes is very hard to tease out from the historical record. There's absolutely a huge earthquake suggested about 500 years ago west of Kathmandu, 8.6. There was an earthquake in 1833. Its exact location is hard to pin down within this area, but it was followed only 30 years later by an earthquake roughly the same location. So again, you maybe got a couple of earthquakes that are close together, not necessarily one year after the other, but maybe just a few decades after each other, and they may be coupled in that sense. There's also the 1934 earthquake, magnitude 8.1 further east, and this is the sort of pattern that we got where the slip occurred in 2015. But the worry is, do we get another repeat here because the pressure's been building up for 140, 50 years? And what about the bit out here? And eventually, when does this need to go again as well? Because it's been quite a long time. Does this go every 500 years or 1,000 years? It would make a big difference to how soon we thought the earthquake would be. But there are large areas, you see, we just don't know. It's unlikely that this exact same area will break again because all the pressure has been released. But the pressure being released here pushes on the edges. So all the bits surrounding it now are a bit more dangerous. Plus, the collision is ongoing. India's still pushing into Eurasia. It's still building up pressure anyway. So it's going to get greater and greater through time. So just to sort of summarise then, where our sort of understanding of the fault model, the earthquake ruptured this deeper portion here, between this deeper bit north of Kathmandu. This bit here did not break. Okay, we only see a little bit of deformation up here, but not a lot. This whole bit of fault is locked, but hasn't ruptured. So it ruptured this flat and ramp part. The ramp sort of builds the topography, but we don't see these older faults moving either. So the older faults are probably dead and gone. It's these ones near the front that are moving, or will move. And there seems to be some control on how far this fault went up, and potentially it could be a damage zone, a bit like that other example I showed you, where another fault may be intersecting the main fault plane and it's caused a damage zone, so the rupture can't get through in one go. It could be something like that. It could be another ramp, could be a different structure that's just stopped it temporarily. And also those sort of where the energy was released in that earthquake, it seems to have actually run along this bend in the fault. It was often thought that maybe it was actually down here where there was a transition between the stable sliding and the lock. But actually it might be a geometrical thing. It's where it's struggling to get up the ramp and over onto the flat during the earthquake in the tens of seconds it takes to rupture. So just some conclusion slides then on the potential for the future. This is a work done by Bilham and Wallace trying to address what the deficit, the slip deficit, how much pressure is built up and how much slip you need to relieve that pressure along the Himalayas. Here are the past earthquakes, roughly where they're known for the older ones. And here's the sort of size that might be expected if that bit of the fault went in one go, how big it could be. So this was done before this earthquake, before the 2015 in here, where you might have predicted something between, well, not predicted, but forecast 7.4 to 7.9 earthquakes. But there are other segments that have been building up pressure for really quite a long time. So this bit where the 1505 was to the west is 500 kilometers long. It's not broken in 500 years, and that sort of area is building up, the shortening at 20 millimeters per year. So that gives you a slip deficit of 10 meters. That's the sort of how big this bar is. Okay, so a lot of these need to move 10 meters to catch up with the pressure that's been building up. And you can see there are many segments along here. What we also don't know is whether these segments are stable. Do they always break like this, or are they shorter or longer? Shorter ones will probably have smaller earthquakes, but longer ones could be a lot bigger. So this area has certainly been capable of magnitude 8 pluses in the past, and there's certainly enough pressure that's built up to do it. And just to show you another example of a small earthquake that was then followed by a big one, the 1950 event here in the east was preceded 3 years earlier by a much smaller event. Okay, so the sort of timescales between these earthquakes could be years, decades. It's hard to get the interaction between the stresses between these different fault ruptures, but that could be the timescale we're looking at. And then also to compare it to, I mentioned the Kashmir earthquake that was smaller than the Nepal earthquake but 10 times more fatal. That occurred here at the western end. Why that was so? It's the eighth most deadly catastrophe in the last 50 years or so, killing 75,000 people or more. Caused a huge amount of destruction, and here are examples of the landsliding as well. And the difference why this was much worse given its size was where the slip occurred. So if you remember, I showed you we were finding about 4 meters on average, 8 meters maximum slip in the Nepal earthquake. This was very similar. On average it was 4, had peak of 8 meters. But the big difference is this was on the shallow portion, the upper 10 kilometers. Last year's Nepal earthquake was on the lower, below 10 kilometers. This was on the higher bit. So having about the same size earthquake, much nearer the surface, and actually this one broke the surface. There's a massive fault scarp that moved the sort of 8 meters. Gives a lot stronger accelerations. You're flung a lot more violently because the slip comes all the way to the free earth surface and flings you much harder. So that would be much more catastrophic even if it was the same size of earthquake, another 7.8, if it was shallower. It'd be a very different story from last time. And just to show the sort of fatality rates from a couple of recent earthquakes further north, Yushu on the Tibetan Plateau and Wenchuan in the far east part of the Tibetan Plateau. If we look at the number of people that were shaken violently and then the number that died from it, these sort of events have a huge fatality rate. If you're shaken very violently and you're in construction, okay, that is not seismically resistant, so if you're in mud bricks, poorly done buildings, then you get a much higher fatality rate. And if you compare where the Nepal one was, this had accelerations, if you remember I said, about 0.2 G, so about 20% G. It was down here, so you can see that you wouldn't expect most buildings to collapse because the accelerations weren't fast enough in the Nepal earthquake. But if it had moved, you know, if the shaking was stronger, you would have lost a lot of the buildings. And you would have seen fatality rates much higher. So what can be done about this? Well, there's a brilliant organisation, the National Society for Earthquake Technology, NSET, that's been working for many years before the earthquake on trying to retrofit things like schools. Those being reinforced actually survived very well in the earthquake. And they also produce on their website a huge number of pamphlets and instructions for how you can better reinforce your buildings, as well as a whole suite of preparedness for earthquake emergencies, the kit you need, what to do with your family before the next earthquake. It's all about preparedness. We can't tell you exactly when the earthquake's going to go, but the odds are in your lifetime, your children's lifetime, you'll get another big one. So you've got to be prepared for it. So this is a brilliant web resource for all of this. They go through in detail some of the building things, best practices for masons, how they can reinforce the structures or build them better in the first place. And it produced scenarios before the earthquake 10 years ago, a sort of earthquake risk plan. So this was done before last year's earthquake, and I'm sure it helped save many lives by having done it, but it needs to be, I guess, more extensively viewed again and taken up in case there's another big earthquake. And there are scenario plans and things that have been put in place by many organisations, and it just requires that there's an uptake from the communities to use these kind of resources and also engage and try and improve them, and for people to say what they want and what they need better. So my conclusions are, despite this being a major earthquake, its magnitude was actually relatively small for what you can get in the Himalayas, unfortunately. Also, the time of day was midday Saturday. Kids weren't in school. People weren't necessarily in the buildings during the daytime like they would be at night. And there weren't those large ground accelerations. The slip rupture was quite a gentle slip pulse. It didn't make the high frequency shaking, only the low frequencies. So given that most of the buildings in Kathmandu are relatively low rise, not many of them collapsed. If you had higher frequency shaking, more of them would have done. And the rupture was buried at depth. It was deep down, deeper than 10 kilometers. It wasn't a shallow rupture. So the shaking was less, and it also means it's going to be hard to find records of these earthquakes in the past from that technique of paleoseismology. So the concern, many parts of the fault system are still of concern, the bits east and west of the rupture zone, and also the shallower portion, the bit up dip south of Kathmandu hasn't ruptured. If it was to go in a similar magnitude earthquake, it would have a bigger impact both on Nepal and northern India. And because we can't predict exactly when these earthquakes are, these are only rough forecasts of using anecdotal evidence, patchy historical records, what we can measure quite well today, but not what we can measure well in the past. All we can suggest is that preparing for the earthquakes, retrofitting buildings seems to be the best practice to coping with what will be inevitable over a long enough period of being there. So I thank you for your attention, and I welcome any questions you may have. Thank you.
Thank you, John. That was really informative, and the way it built up from general information towards the recent earthquake, I was really impressed, and I enjoyed it. And we open the floor for a few questions we may have. Is there any questions?
Yes. I'm interested in how much influence MSET has on the Nepali government.
I'm afraid I can't comment directly on that. I have colleagues who would be able to answer that, but that's not something I've been embedded in. It's part of the Earthquakes Without Frontiers programme. There are various researchers, both Cambridge here and in Durham, who actually interact directly between NSET and are actually trying to map those interactions. That's part of that part of the study. I mainly focus on the science side. I can certainly give you their names later on, but it's not something I could answer.
Any more questions? Yes.
Well, it was very insightful. But I was wondering that all the data you showed are taken from the satellite with the GPS, which was on the surface of the ground. Right? I was wondering if there is any technology that is embedded inside the Earth where the actual thing is happening, and would that, if there is not nothing as such, would that make any difference, or would the data that might be collected from such a port be same as what you get from these radars?
Yes, unfortunately it'd be great to actually be on the fault at depth. The only problem is it's very hard to drill through the earth that deep. You can drill relatively shallow for oil exploration, maybe a kilometre, 2 kilometres. Some of the deepest drills have gone many kilometres down, but it's very expensive to actually instrument. So places like California and Japan have done that on very rare occasions. There's a scheme, the SAFOD for the San Andreas in California, that have done that to actually look at the fault rock material. But most of what we get is remotely sensed, either of the surface from the GPS and the radar, or the seismology. Using those seismometers on the other side of the world, you can try and work out what you thought happened at depth, but you can't directly see it. If we could, it might help sort of solve some of these problems if we could actually see which bits of the fault were creeping a little bit and which bits were locked. I think that would make huge avenues, but it's too deep. 15 kilometres is just too deep to be able to do, and is unlikely to be achievable in the medium future even. So we have to rely largely on surface measurements or seismology. Yeah.
Yes, Pramila.
It's very interesting, thank you. I was stopping a few first of your slides actually. I was wondering, so what determines the movement of the plates and the direction where it's going towards? And do all the Eurasian plates also are also moving, or is it just the Indian plate moving towards the Tibetan?
That's a good question. They're sort of understanding the driving mechanisms of the plates. For the case of India, I mean, they're all sort of coupled together, but it's often related to the subduction of a slab. You've got a couple of forces in the system. You've got things sinking and pulling, and then at the ridges where the sort of deeper mantle flow is pushing them apart, you've got a ridge push. So they're the sort of main things in your system, as well as forces within the plates. If they're really high, like Tibetan Plateau is, that can push on the surrounding plates as well. So you get different scales of motion. So with India, that's the sort of case. It's colliding with Eurasia. It was in the past because of subduction of the oceanic plate. I showed you sinking. But it's being slowed down gradually because the force of Tibet's pushing back. You've got some pushback from that. The other plates that were all moving northwards, there were Africa and Arabia as well, similar situations. There used to be a very large ocean there in the past, so that was all a similar sort of system, and they've all bashed into Eurasia. It's a bit slower in other parts. India's 40 millimetres per year at the moment.
Just to add on the same question, I was wondering about that as well. So the origin of these plate movement is down to how the Earth was formed and the way the Earth plates are releasing the energy. Is that correct?
Yes. It comes from the heat engine of the sort of mantle. You've got energy in there, the heat, and the plates sort of are going from hot to cold. That's in essence the density thing. What's dense and cold drags down, and what's hot is buoyant. Okay. That's the main sort of flow. It's argued how long in the Earth's 4.5 billion years, how long have we had plate tectonics as we recognise it? Did it start very quickly when the Earth was a lot more molten, or did it take a long time before you got it quite solid? So all the plates are pretty solid. They're only small pockets of melt related to volcanoes. They're largely pretty rigid.
Okay. Yeah, it's interesting. And the question I was going to ask was, are they ever going to stop, or is it linked to the existence of the Earth itself?
It is linked to the sort of the heat budget of the Earth itself, but they would eventually freeze up. I couldn't tell you which wins out first, because you've got the sun that's going to expand and die on a sort of billions of year time scale. Yeah. And whether the Earth will cool fast enough to actually stop the plate tectonics before we get engulfed by the sun is. Yes. I should know, but I'm not sure which way.
Yes, let's take another question.
You mentioned about the another big earthquake in our lifetime, which is about 20-30 years. It was based purely on the historic data, or you have some kind of technology or some techniques to sort of measure that timeline?
There's no technology, there's no technique to give you an exact date. All I can show you is this sort of build up by many researchers, these anecdotal evidence of examples where it can be decades rather than centuries between earthquakes. It's not an exact science. We don't have enough data to constrain it. Maybe if we could go really deep and examine these things, but we can't. So I think certainly in the short term, we're not going to be able to give you that kind of useful information of 30 years' time. But you've sort of seen the range of timescales there that would lead most people, I think, to be concerned enough that in their lifetimes, somewhere in Nepal, you could quite easily get another big earthquake.
Yes, Alex.
Just a generic question. You said in view of preparing before the earthquake happens, we've been hearing about this animal behaviors changing before the earthquake happens, like dog barking and the birds flying here and there, and also this dolphin behaviors changing. Is there any way to relate these kind of animal behaviors and maybe learn something from them to prepare in advance for the earthquake that it's coming out?
This has often been sort of anecdotally said after an earthquake. Nobody has yet found a reliable way of measuring animal behaviour and conclusively showing that those animals were doing it before the earthquake because of the earthquake. Until we can find a link, most of the things you can't believe that they're related, because it's always said after the earthquake. They don't seem to be a very good predictor. We certainly don't understand the behaviour of animals enough to rule it out completely, but it seems unlikely to be a useful way to do it, even if it were to be a real phenomena. It could just be people's sort of trying to match things up after an earthquake to try and explain what might have happened.
Yes.
Immediately after the Nepal earthquake, there was a lot of discussion as to whether it was an earthquake or what was called a classquake. If it affected people who couldn't afford to build houses with sound engineering and such. Do you agree with that or not?
I mean, that's getting into the sort of social sciences side of this problem and things we're trying to address with this. As a natural phenomena, it was an earthquake. Its impact as a catastrophe is that intersection between a physical event and society and its vulnerability to those events. And it is, as I showed you in that picture, the death tolls are often related to the parts of the world that haven't got been able to afford to retrofit the buildings. And in parts that are richer, it's more a problem of economic losses as opposed to catastrophic loss of life. So there is definitely an economic problem there. There's a problem with corruption often in countries as well that mean that even if there are building codes, they're not enforced, and corruption often scales also with economic development. So there is a sort of economic class angle to the impact on the individual. And eventually, the earthquakes will always happen, but as humanity is suffering from them, eventually that should go away. But the earthquakes won't go away, just the impacts.
Yeah, I had a question regarding the oscillation movement you showed in one of the cameras, CCTV, and the movement, the pattern of movement. It was in the basin, lake basin, and you said it was the nature of the basin that was causing that type of movement compared to that outside the basin. Does that mean that the basin is vulnerable to more damage because of its movement and the oscillation? And to tag with that, there was a rumor or fear of the whole ground in Kathmandu going liquefaction. How is it related? Is Kathmandu more vulnerable to earthquake-related damage compared to other part of the country because of the lake basin, or it's just one of the phenomena that occurred?
Yeah, no, it was certainly felt before that there was a big worry about the basin resonating, shaking like that, and the liquefaction before. It was expected to be a lot worse than it was. It wasn't in this event. The resonance comes from the seismic waves coming into the basin and then bouncing off the edges. So instead of carrying on through, they bounce back across the basin. So in this event, it did that a lot. You saw those big amplitudes, but it did it at the frequency that didn't destroy the buildings. The concern would be another rupture that didn't tear the fault in quite as smooth a way, but did it in a much more jarry way, would generate the kind of waves that are higher frequency that would then also be amplified in the basin, but also damage the buildings. Because the problem with the amplification and the resonance in that basin is the waves can coherently build up to be bigger and they last a lot longer. You saw that if you've got 6 backwards and forwards for 4 seconds, that's half a minute's worth of shaking rather than a pulse that comes through for just a few seconds and then the shaking stops. So as a building starts to fail and resonate, the longer you're shaking it, the more likely it is to collapse as it sort of tunes to that shaking. So yes, it would be a concern in another earthquake if it's higher frequency, because it will rattle around in that basin. But you still get strong accelerations on the high topography as well, those ridge crests, where I showed some of the big damage to villages. You do get strong accelerations in high topography as well, plus a lot more landsliding.
Yeah, let's take the last one.
I have 2 questions. I think that it's University of Berkeley, California. They're developing an app based on GPS, and then you could, after it, of course, it's after the earthquake happens, then it will tell you. It's like your phone working as a seismic meter.
Yes.
I think it will benefit.
Yeah, so those sort of technologies, you've got this sort of retrospective where it tells you afterwards, so maybe scientists can use your data and then learn a bit more after. But what would be even more useful is to use that as the rupture's going on. I showed you in the case of Nepal, that earthquake took 70 seconds. So imagine people in the West had the phones and it was connected to a network and a computer server, and it started shaking. Unfortunately for those people, there's not a lot that you can do. If you're right above the earthquake, it's too late. But if those instruments, your phone, could send the data fast enough, and it does it often near the speed of light, you can tell people at the other end of your country that a rupture's coming. So that's what they're definitely trying to do in California, and would be very useful to roll out everywhere, because the kind of ruptures in the Himalayas here are very long. You can get many hundreds of kilometre long rupture, so that would be incredibly useful for the people at the other end. Just to have seconds to duck, cover and hold is what you need to do. So.
All right, so the last one.
Do you think global warming or climate change has anything to make any difference in earthquake?
No, there's not a strong correlation with that. The closest thing you get is some deglaciation of high topography that's been argued that could have an impact on volcanism, but that's a very contentious area. It would need more research to nail that. And you know, there's an ongoing continuous risk here anyway, and that's increasing because of the vulnerability of people, not necessarily earthquakes becoming more common. They don't seem to be. It's the amount of people and their vulnerability that is.
With that, we'd like to thank John for being here, and thank you for staying this late. This video of this presentation will be in YouTube, so if you have asked questions and you think you have been captured in video and you don't want to be shown in the YouTube, please let us know and we'll just crop you out. Other than that, we would like to thank you very much.
Thank you.
Let's thank him.
Yeah, thank you very much. That's great.